Today's lecture is called Have you tried turning it off and on again? To deal with errors, you need to first detect the error scenarios, which is fairly obvious. So let's just list up the things that can go wrong in our program. So first we have the expected reasons. Well, if we've programmed our program competently, then the things that we have written obviously won't fail because we have written them properly. So the only things that can fail in our program, hopefully, are the external things. For example, networks, we can't connect to a network. Files, there are no files on our file system because our file system doesn't exist or something like that. Memory, malloc returns a null pointer if there is no memory, for example. And all of these things, they're handled with normal exceptions or error returns and so on. So you're hopefully all familiar with dealing with these kinds of things. In writing your network code, you've gotten errors like connection refused or address already in use, or if you're dealt with files, file doesn't exist, and all of this stuff. These are the expected problems, but of course, as competent developers, there are also unexpected problems because, well, sometimes we have bugs, and bugs can come from multiple sources. There are these algorithmic type bugs where we haven't implemented our program properly, and then there are more specification type bugs where we've misunderstood the specification or the specification wasn't complete and it's not implemented incorrectly, it's just not implemented in the first place. And then the question is, okay, we've deployed our program, it's missing some things, there are some bugs in our program that has been deployed. How do we deal with these kinds of errors? Well, it's too late for testing because we're in deployment now. So we need, ideally, if we want to create the ultimate within robust software, we want to handle errors that we don't expect, don't know about, don't have reasonable ways of checking for. So this is error handling in this course. It's not just check your error returns and your program is fixed. It's not that easy. So let's try to develop a new way of thinking about error handling. So we have the three observers of our error, which is the first one is the developer. As the developer, we have bugs that we want to fix, so let's fix the bugs. So we want to have a mechanism that lets us quickly identify exactly what the bug is and then also implement fallback strategies for when the bug occurs inevitably in production. And also for the expected failures, we want to deal with the expected failures in a reasonable way. And then the user of our program, well, the user, if something is wrong with the program, there's not much they can do, but at least they want to see a sensible error message. But there's not much more they can do other than turning it off and on again. And then the last observer is the program itself, which is a bit more of a subtle observer. The program can observe its own failure to execute properly if we've programmed it properly. But really, if the program fails to execute properly and it identifies this, then really the best thing we can do is try to want to continue. It's like, well, continue or see if we can maybe even ignore the errors and just say it's fine, we can do something else instead, or some other kind of self-healing mechanism. That's what we really want. And if we're implementing some new way of thinking about error handling, then really, ideally, we want all of these things. Ideally. So that's like the high level. These are the things we want. This is the specification for our new way of thinking about error handling. So let's look a bit more closely. For like when we're developing it, we want to write the code that does this, and we want to have a developer focus on how we actually create such software. So we want some kind of unification. We want to unify the things that we expect to go wrong and the things that we don't expect to go wrong and handle both of these things, preferably in the same way, so that there's less code to write. And we also, we want to handle all of the things that go wrong. And we want a small amount of code because, well, we're primarily focused on writing the things that should do the happy path, the things, writing the code for how the program should execute when it's functioning normally. That's usually our primary focus, and that's often quite hard as well. There's some algorithm involved. There's lots of things interacting with each other, and we don't want to write 50% error handling code and 50% normal code. We want to edge more towards 90% or even 100% normal code and write as little error code as possible so they don't intermingle and it looks like yuck. So the less error code that we need, the more likely it is that it's written. If you need to write 90% error handling, you're not going to do it. It's also more likely to be correct because the more code you write, the more interactions there are within the code that you write. And also the less of it there is, usually, well, the less mental overhead there is in making it. So less code is good. So that's our desires. Let's look at, we want to identify expected failures and unexpected failures. So let's see if we can identify unacceptable behavior in our program in some sensible way. So we have some operation. An operation is a function or a program or whatever, some piece of code that is executing, which has an input and a result. And this operation has two outcomes. Either it works as we expect it to work, or it does not work as we expect it to work. And then we have a detection mechanism that detects the workingness of our operation. And this detection mechanism also has two outcomes. Either it accepts the operation, or it rejects the operation. So there's a very obvious figure that we need to write now. We have 2 dimensions with 2 booleans. Obviously, we're going to have to create this figure. So here we have 2 good outcomes here, which are top left and bottom right, which is the correct identification of working or not working code. And then we have this one in the top or in the bottom left where the operation doesn't work, but we accept the operation. And in this scenario, we have accepted the buggy behavior. So we want to avoid this scenario. And then in the top right scenario, we have one which is a bit more subtle, which is that if our detection mechanism for accepting operations is too trigger happy, then we might accidentally reject correct operations or working operations. The code works, but we still reject it. So this is not ideal, but it's at least, this is acceptable. It's erring on the side of caution instead of erring on the side of minimal amount of detection. So, as you might see, this is a kind of a type 1, type 2 error scenario. We want one of these and not the other one. Which one is type 1 and which one is type 2 isn't, well, it depends on your perspective in this case. So, what does traditional error detection do? Like, a function returns an error value or throws an exception. What does it do? Well, it detects failures. And detecting the expected failures, well, we expect them, so detecting them is reasonably easy. But detecting unexpected failures, like bugs and so on, is hard to impossible. We have the acceptable scenarios on the top, and then we have the unacceptable scenarios at the bottom, and then we nibble at the unacceptable behaviors until we've hopefully grouped all of them, and we have only the acceptable ones left. But the problem is that we can't do that because there are these unmodeled, unacceptable behaviors. So instead, we take a top-down approach. So instead of detecting failure, we try to detect success instead. So detecting expected success, well, again, that's easy. And detecting unexpected success, well, what happens if we don't detect unexpected success? We reject unexpected success. Well, okay, that's, again, it's not ideal, but we can live with this. So the approach is, instead of a bottom-up approach, it's a top-down approach. We're taking all the acceptable behaviors, and we're nibbling away at all the acceptable behaviors until we're left with all the unacceptable stuff and possibly some other acceptable stuff. I also just want to comment on the word or the phrase or expression or terminology of acceptance test, because this terminology is used, well, we use it as a runtime way of thinking. We're testing the code while it's running, but I'm seeing it used a lot elsewhere as we're testing the program before we ship it. So like the factory acceptance test and so on. So the terminology today I am using acceptance test purely as a runtime term, not as a development time term. So now we figured out that we want to identify success and we don't want to identify failure, because identifying success, it gives us more room for maneuvering. So let's look at how these detection mechanisms work in code. So let's first start with good old-fashioned error returns. And we're just going to look at how error returns work. You've all hopefully seen error returns before. So let's just look at an example of traditional error detection, and it's from the Linux source code. So this is mounting some file system operation deep inside the Linux kernel, and I don't want you to read the code itself. Don't focus on the text. Focus on the structure now. So this is where the interesting stuff starts to happen. We do some operation, and then we check if the operation succeeded. And if it didn't succeed, there's a goto. We perform the next operation, we check for success, and if it didn't succeed, we go to some handling. So this pattern continues. And then eventually, when we receive the bottom, or when we get towards the bottom, there's still some more ifs and some more gotos here. This is the bottom of our function. So there's do the things. If the success or failure, we break at the first point of success or the first point of failure, and then we go to the least amount of handling in order to deal with that failure. So if the first thing fails, we jump to the bottom of the function. If the next thing fails, we jump to the penultimate goto, and if the third thing fails, we go to the third goto at the end. So success scenarios and then failure scenarios, but written in the opposite direction. So let's look back up at these ifs. Imagine how you would write this code without the use of goto. How would you do this? Well, instead of having if it fails, go to error handling, it would have to be if it fails, do error handling, but we still need to do the error handling for the next failure, so we'll have to turn that around. So instead it will have to be if it succeeds, continue inside the if expression, otherwise do the error handling, or not otherwise, but well, it would be otherwise as well. So you'd have to have a flag to store the error state as well. So you'd have to have these nested ifs for operation, if it succeeds, next operation, if it succeeds, next operation, indenting every way, and then you'll also have to store a flag for the erroriness of the operation so that you can undo it afterwards. Doing this with ifs, holy fuck, this is going to be an absolute mess. So there's this meme that was started in 1968, go-to statement considered harmful, paper by Edgar Dijkstra. And he wrote, well, this was before decent programming languages existed. So could go to literally anywhere in your program. It was basically a jump in assembly terms. Go-tos in C can't go to literally anywhere. They can only go within the current scope you are in. So in this case, the function. So it's not a completely arbitrary go-to. And they have labels. And you can give them sensible labels. So go-to considered harmful? Yeah, fuck that. Go-to considered extremely elegant if used appropriately. So the important part here is, if you were to do this with ifs, your data flow, you would need these extra flags. The data flow it's not top to bottom. We're not doing operation A, operation B, operation C. We're doing operation A and then indent operation B and then indent operation C. And the data flow goes in a different, it looks yucky. So notice how let's look at this data flows. This is what an error return does. It returns a result, and the result goes out, or it goes downwards. So the input comes in from the top and the result goes downwards. And then the error return, if it returns an error, the error value is stored in a variable, and that also, in order to handle it, your control flow continues to go downwards. With exceptions, and hopefully you're all familiar with exceptions, the error flow goes the other way around. It isn't stored in a variable and then you check the exception value. The exception is thrown and then it bubbles up to whoever calls it first. So the traditional way of dealing with exceptions is to wrap the thing that can fail in a scope, which you've labeled with a try statement. So it's try the things inside the scope, and if it fails, it bubbles out of that scope and then it reaches your catch statement. Or if you don't have a try catch, it bubbles up to whoever called that function and they have to try catch. So if we're doing error returns, our control flow goes forwards. So we used goto in order to go forwards in ways that we can't do with an if or a for or a switch. So if we're using exceptions, well, then our control flow should go backwards. Who knows about control flow operations that go backwards? Because you probably haven't used any of these before. Maybe some of Go people have used one. This is how you should deal with exceptions. If you were to do that kind of thing with exceptions, the previous Linux example, with exceptions, it would look like the thing on the left. Everything in blue is the exception handling code. That's the thing we don't want 90% of. It's the thing we want 10% of. This is how you would have to do it with exception handling if you're going to use try-catch. The thing on the right is the way, this is how you do backwards control flow. So the undoing is written upwards and the doing is written downwards. So this kind of scope failure, scope exit, and scope success, in Go you have defer, but you don't have defer that switches on success or failure. But this is D code, so you can do this in D, obviously. And you can also do this in C++, but you'll have to copy-paste the macro written in Andrei Alexandrescu's modern C++ book. It's a macro template hybrid abortion thing. It looks like absolute ass, so you just copy-paste it once and it works. This is how you deal with exceptions. You want the control flow to go in the same direction as the data flow. The data flow is bubbling up from outside scopes, so your control flow should go in the same direction, which is backwards. So let's now talk some shit about people who don't understand how to do error handling at all. Apologize to Raymond Chen, but your blog post was the first one I found. So it doesn't, well, he's probably a fairly competent programmer, and we all no, 2004, he's had a lot of time to learn from his mistakes. Hopefully he has. Okay. Here's an example from a C# book. This is the thing he's trying to talk shit about this thing, and I agree. You would talk shit about this. You try some generate database function, and the generate database function does three things. It creates physical database, creates tables, and creates indexes. Okay, each one of these three can throw an exception. And we have a single try catch which catches one of these three exceptions. So any of these three things can go wrong. You see what the problem is, right? Depending on how far we have progressed, we need to undo some amount of work in case it fails. So the generate physical database, it allocates some storage on disk in a file. So if we don't undo that, then we'll have a file that is never used again. So we don't want to do that, because eventually we're just going to run out of disk space for no reason. create tables, do we need to undo the table creation, or do we need to not undo the table creations because they haven't been created? And same for indexes. Like, how far do we have to unwind? Well, we have a single try catch, and we need to figure out how much to unwind. Well, we're doing multiple operations, and we only have a single error handling operation. Obviously, this is wrong. It's not going to work. So that's his comment as well. Important information was lost. The state of the database creation. The code that catches the exception doesn't know which step in database creation it failed. Now, this is a complete fucking strawman argument, because you can do the exact same thing with error returns. If these three things returned an error return, and then you just took a logical OR between all of the error values and returned that one, you don't know which thing failed. You just know that one of them failed. So you can do the same, you can write shitty code with error returns too. So that's not the fault of exceptions. So, sorry Raymond, you're wrong about that. Writing correct code in exception throwing model is in a sense harder than error code model since anything can fail. Well, okay. In error code model, it is obvious when you have to check for errors. Okay, how many of you here have actively checked the error return value of printf? How many of you have actively checked the error return value of pthread create? He has. Of malloc, or do you just assume that it's not null? Yeah, it's only site that has actually checked it. Oh yeah, we have one guy, but he's a Russian exchange student. Are you not? Or you're an exchange student. Yeah. Where are you from? Spain. Spain. Okay, I mistook your accent. Okay. Well, apparently they learn about how to deal with errors in Spain. So good for you guys. So, well, it's like this again. Yes, it's obvious that you have to check for the error if you're doing error returns, but yeah, people have a tendency to just like say, fuck it, it's fine. When you get an error code, well, in the exception model, you just know that the error can occur anywhere. So, well, there's the drawback of the error returns is that, no, well, the drawback of exceptions is, yeah, you don't know where it happens, but the advantage is that you can't ignore it. So you lose some, but you gain some. So here, okay, let's talk some more shit. Consider the following. Go, guy, add new guy. There's some team game, 2 teams, red team and blue team. So he's creating some new guy to a league, and then is adding the guy to a team. Okay, so is added to the league, and then is assigned the teams, and this choose random team can, for whatever reason, it can throw an exception. Okay, well now we have some guy that has no team who was added to the league, and that was undesirable. So we need to unadd him from the team. So what do? Well, again, the obvious fix is to make sure that we don't commit data, we don't add him to the league before we've assigned the team. Fairly obvious. General design principle, don't commit data until they are ready. You've heard this one before. You've heard this last week. This is a core function and a shell function. Choose random team, this is a core function. It doesn't need to apply any state transformation, it doesn't need to apply any output. Add to league, we're sending the guy to the league. This is an output, this can therefore fail because it depends on the league existing. So this is an external dependency of our process. The guy creation process, it can fail internally, but it won't affect the outputs. It won't affect the world state in any way unless the choosing random team function succeeds. Don't commit data until they're ready. Good, Raymond. Good work. Okay. In the real world, things are a lot messier. Consider the following. Choose random team. Okay, this thing can fail. In this case, we want to add we don't just want to have the league table, but we want to have individual team tables. So we're adding him to the team table, and we're also adding him to the league table. But adding to either one of these two can fail and throw an exception. So we have this add new guy function, Adding him to a team, that can fail. And then adding him to a league can fail. And if this fails, then he's added to a team but not to the league. And that's undesirable. And of course, it just ends with rhetorical questions like, what consequences does this have on the function's correctness? Now, the goal in this course is that you are eventually going to end up being smart enough to realize that this piece of code, regardless of if we have to handle errors or not, this piece of code is fucking stupid. That's the goal of this course. Let's look at all the ways in this is stupid. So let's go back to the PowerPoint. And there we go. Exceptions the wrong way. Let's spot all the things that were wrong with this piece of code. First of all, it uses try-catch instead of a proper scope deferment statement. So the control flow for handling with the exception is going forwards, but the exceptions are going backwards. So that's fundamentally using the wrong mechanism to deal with errors. Also, he applies state transformation in these incremental steps. So he's adding to a team first and then adding to a league. So it's two transformations to the outside world, and one of them can fail, and we want to actually apply both these transformations at the same time. So, well, first of all, if you had split this into a core shell operation, then the shell thing that we're doing is a single message to one thing. Also, this is an object-oriented abortion where he's invoking behavior in other components. If you had just sent a message, then it could be accepted or rejected based on the different criteria. So you have a league process and a team process. Well, if you sent it to the league process and then the league process sends it to the team process, then it would be much easier. Really, the fundamental problem here is that he's duplicated the data. He has this team table and then he also has a league table. So either don't duplicate the data, or let the duplication be okay. You can be added to a team but not in the league. Or you can be added to the league but not in the team. Why is that a problem? If this is a problem, don't duplicate the data. You don't need to have the data duplicated if this is such a big deal. If it is such a big deal, then you don't want to be able to represent the inconsistency in your data structure. It's just an absolutely useless duplication. And if you absolutely do need the duplication, don't blame the error handling. You're doing transactions. And you're doing transactions with multiple things that can fail in a single try-catch. And you're like, yeah, this doesn't work. Yeah, it wouldn't work with error returns either. This is just complete straw man. If you write the code sensibly for the happy path, the amount of error handling that you have to do in the unhappy path is the magnitude of it is so dramatically reduced. This problem wouldn't be a problem if you couldn't, if the inconsistency in the data structures were okay or it was a single data structure. That would fix the problem. And it would also fix the problem if you didn't try to invoke behaviors in other components. If you had just sent a message to these things, and the only thing they have to do is update their own internal state representation, that wouldn't be an error. So let's look at the mechanisms that we have available to us in the languages. Well, the happy path, it uses standard control structures, which are like if and for and switch and whatever. Error scenarios are when we can't follow the happy path. If we've used all the standard control structures in the happy path, it makes sense to use the non-standard control structures in the non-happy path. Because we're breaking the flow of the program because something wrong happened. In order to break the flow of the program, we have to use non-program flow constructs or non-standard program flow constructs. Which really means that things like goto is absolutely not the enemy. It's the elegant way of doing this. So, we now have mechanisms. We now have a desire for the things that we want to detect in our program. We have the language mechanisms for doing detection or just creating code paths for success and failure. let's see if we can write error handling in the sensible way now. So let's look at how writing acceptance tests, or how acceptance tests would look like. I'm going to come with an example after this slide, but here are some general guidelines. Just use assert a lot. Or if you don't have asserts, just use an if. Check if the return value of a function is sensible, or check the integrity of the data structure. And if it isn't, use a if for a forward flow, or use an assert for a backwards flow. Checking the integrity of a data structure is usually fairly easy to write. The logic for this is usually not that hard. They're pretty low effort, because just saying this must be true, especially in the case of asserts, so saying this must be true, and then you're like, okay, that's the error handling, that's the error detection done. That's fairly low effort. There's not a lot of code you need to write. There's no extra nesting, no extra indentation, none of that extra stuff, no extra variables. And also, finally, of course, it doesn't look like dog shit, which this kind of nested if control flow goes through this nested if when we have a bunch of extra variables and flags. Nobody's going to want to program that, and that's why people don't check the error return values on most things. So let's just look at an example of how acceptance tests could look like. I've struggled to find some really great ones, so I'm just going to use one from then that I wrote myself, and this is in the simulator source code. So the top example with the invariant, the simulator data structure must always satisfy these constraints. And these are checked every time I modify a variable in the simulator state. It just checks these constraints to make sure I haven't done anything stupid. And this was incredibly useful during development, because it allowed me to sort out a huge amount of bugs. And also for this floor arrival event, when I arrive at a new floor, I just want to make sure that I haven't received a completely absurd floor to arrive at. So I have things like, we didn't skip a floor, which is the bottom one, or we didn't arrive a floor in the opposite direction that we were traveling in. So we're going upwards, and then we arrived at the floor below us or something like that. That would be weird. Again, these were incredibly useful during development, and now the program is deployed. Well, they haven't been triggered in many years now. The simulator has been stable for quite a while now. So this is how you would write acceptance tests. That's fairly straightforward. Yes?
What is the difference between if and assert?
Well, the difference between, if we're going to do, the difference between if and assert. If we're doing assert here, it just checks if this is true. If this is not true, it throws an assert error, which is like throwing an exception, and it will bubble up to the outside scope. So the control flow would go backwards. So we're going to get to, this is just a detection mechanism. If we're doing it with an if, well, we're detecting that if this is not true, then we handle the error in another way. So the question is really, if we're doing an assert, the detection mechanism, or the triggering of the detection mechanism will make this bubble upwards, and if we're doing an if, the triggering of this detection mechanism will make it bubble downwards. So it comes down to the handling. How do we do the handling? So good question. Next slide. Handling. How do we handle the unacceptable? So what do we do when the assert triggers, or what do we do when the if triggers? That's the question. Well, in traditional error detection, it identifies exactly what goes wrong, but the acceptance test just identifies that something had not gone right, which leaves us with, well, it gives us a few things. It gives us where it didn't work, which is useful for the developer. It gives us a file and a line count and so on. And hopefully for the user of the program, it also prints out a sensible error message. But there are some things that we still don't get. Exactly what the origin was of the error, which is something that traditional error detection with checking the return value and checking the exception, that would give you exactly the source of the error, as long as you check everything. And it also doesn't give us this recovery mechanism that we really wanted. So what we want still is, well, we can't get more information about what originally caused the error, and, well, it's too late now anyway. And what originally caused the error could be a bug, which we can't fix. The program can't fix its own bugs, usually, unless it's some Erlang miracle. So the question really is, how do we self-heal from an arbitrary failure? Because we don't know if this was caused by an external dependency failing, which was an expected error, or if it was caused by a bug, which is an unexpected error. So we want to self-heal from this arbitrary failure. The question is how? Well, let's rephrase this question and see if we can get a better answer. What is the worst unknown arbitrary failure? I would say it's the program in its totality crashing. It just completely stops working. That would be the worst case arbitrary failure. Or perhaps even worster case, the crash propagates and it infects a bunch of other things and it crashes like a domino effect. It crashes everything around it. That would be even worse, but let's go with just this operation crashes. It completely fails. That would be the worst thing that could happen. So, if an acceptance test fails, assert or if, doesn't matter, what do? Well, we uncrash the program. We restart it. That is the general purpose. It doesn't get more general than this. If we can just restart the program, we can mask over most kinds of transient errors. The problem is, what if it's not transient? Well, if it's transient, we can just restart it. If it's not transient, we have a bug that happens every single time, then, well, maybe your program is just a bit shit. So let's look at how do we write restarting mechanisms. We've done the detection, we've crashed the program, or we've had something that's not as bad as crashing the program. If it's not as bad as crashing the program, we can just crash the program. So really, how do we deal with this assert? What do we do when this triggers? What do we do when this if triggers? Crash the program. If it's an assert, just don't catch it. That's the easiest way to do it. If you just don't catch the assert, the program crashes, and then you restart it. As long as the restart mechanism works, you're good. So we need a restart mechanism that works. Well, we need to restart the execution, obviously. In order to restart the execution, we need to detect that the execution stopped. And what's the difference between an execution that stopped and the execution that just doesn't have anything to do? Well, we can't really detect that it has died. We have to detect that it's alive. So this is just a standard. We need an I am alive message that is just sent periodically. And if we lose enough of these in a row, then we say that, okay, it is either not doing anything productive, it is either stuck in an infinite while loop or something, or it has actually crashed. So we need some kind of I am alive message. So this gives us two ways of doing it. Either we have a supervisor that checks that the main program is still running, and then restarts that program if it's not running, or we do the process pair solution, which is the program creates its own clone, which is just passively receiving, and if the primary one dies, then the backup spawns its own new clone and then continues. That's exercise 6. Really, for exercise 6, if you do supervisor or if you do a process pair, yeah, whatever, it doesn't really matter, honestly. I know the exercise says process pair, and it's definitely the more elegant one, but functionally, they're both the same. Cool, we have a basic restarting mechanism. It's literally just telling the operating system to start the program again. Wow, that's not very hard. The problem is, of course, if we restart the program, we lose the progress that we've made. And we don't want to lose the progress. So we need to restart the data structure that's internal to the program as well. So you want to make sure that we continue from where we left off. Or rather, we want to make sure that we continue from the last place that it is safe to continue from. Because if the internal state and the received data combined triggered an error, then we want to make sure that we don't immediately re-trigger the same error when we restart. So we need to go slightly back in time and get some fresh data and see if we can continue with the fresh data and just ignore whatever incoming data that made us fail. So in order to make sure that we start with correct, sensible, reasonable data, the data that we last stored that we can continue from must have passed the acceptance test. Otherwise, it's obviously not useful. So this gives us 3 different ways of doing it. The first one is that in the case of a process pair, we have this checkpoint restart mechanism where we restart from the last known good data. And then we have the checkpoint message way where instead of writing to some checkpoint, we send the checkpoint as part of the message. So the difference is really, where is the checkpoint stored? Is it stored in some persistent data structure, or is it and then overwritten continuously, or is it sent as a message directly to the backup process? Or whatever. And then we have the last one. I'm not quite sure on the terminology. I've just called it persistent, where instead of having some internal data structure that you're changing, the data structure is external. It's a database. So it's a read, modify, write to the database. Now this requires that your database has security and safety and works properly. So this usually requires some amount of transaction mechanism with a database. So perhaps not recommended immediately unless you happen to have a transaction proper database lying around. If you do, cool, just use that. So let's also integrate this with the core shell divide that we've been using many times now. We have a couple things that can fail in our process. We have the expected errors and we have the unexpected errors. The expected errors are the outside world isn't particularly cooperative today. Writing to a file didn't work, writing to network didn't work. And then we have our own program, which was the developer, which is yourself, wasn't particularly cooperative yesterday and introduced a bug. So you failed your own acceptance test. So these are the 2 sources of problems, 2 sources of triggers in your program. So what we want to do is we want to preserve the integrity of our own process so that it doesn't crash, or if it does crash, it can restart cleanly. And we also want to preserve the integrity of everything around us so that the error doesn't propagate to everything else. So you want to not propagate the error more than strictly necessary. So let's look at some guidelines for how to do this. First up, make sure that your data is good, your data is safe before you commit it to the outside world. So put the acceptance tests inside your core functions. Your core functions return what your next state should be. So if your next state is not safe, crash, so that you don't save a next state. And your core functions also return what the output actions should be. So if the core function, again, fails the acceptance test, you don't apply an output action. This prevents it from propagating, and it prevents it from being stored so that your restarting mechanism fails. So do all of your acceptance tests before you apply any kind of output or state transformation. And then, of course, keep your data together when it makes sense to be together, and keep your outputs together when it makes sense for your outputs to be together. Because if you're applying outputs incrementally one at a time, and you need them all to be together, don't apply multiple outputs. Apply one output. So you'll have to restructure your program so you only apply one output. If you can't do this, use transactions. Because if you're doing this, if you're applying multiple outputs and the outputs must go together, and you're doing it without doing transactions, you're doing it wrong. And if you have data structures that must go together, keep the data structures together. Don't spread data structures more than strictly necessary. So this is the same thing from creating testable code. If your data structures belong together, you keep them together. Of course, restarting the entire program is often overkill. And, well, sometimes there's no such thing as overkill, but we might not need to burn down the entire forest when a tree catches fire. So ideally, we want to only crash a small part of the program so it doesn't propagate too far. So if we have other operations going on, we want these to be minimally affected. If they are ongoing, perhaps they can even complete without being affected at all. So if our process that failed does have some interactions with other components, Well, we want these interactions to be modeled in such a way that if the interaction doesn't happen, the program in its entirety doesn't fail. Which means if we are reliant on invoking behavior in other components, it will fail. So instead of invoking behavior in other components, what do? We send messages to other components. If the message doesn't arrive, the component is unaffected. We also want the restarting process to be fast. And obviously the obvious interpretation of fast is like the execution time is low. But there's the other less obvious interpretation, which is that if your program is created in such a way that the startup mechanisms are so involved that it must always be started up in one particular order, you've probably fucked up somewhere along the way. So you're creating a lot of implicit or explicit dependencies between all of your components. If you have this, then doing restarting or doing partial restarting will never work. So fast restarts or component by component restarts requires that your components are not tightly coupled in an untestable fashion. So if we have a bunch of components and these have interactions in the happy path, then obviously they must have interactions in the unhappy path, which is the error handling scenario. This much should be fairly obvious. So if we want to limit the amount of interactions in the unhappy path, what do we have to do? Limit the amount of interactions in the happy path as well. Just limit the amount of interactions entirely. So, again, it's the don't invoke behavior in other components because you're tightly coupling yourself to all of these other components. You're creating this object-oriented hierarchy, which is a pain in the ass to test and it's a pain in the ass to deal with errors in it. So what do we end up with as a result? Well, look, we now have yet another reason why this communicating process model is good for error handling, it was good for testing, it was good for distributed systems, ended up with a lot of state machines, which is a sensible abstraction. We've ended up in the same place again from a completely different perspective. So that's cool. That's really the conclusion. But I just want to say one more thing. And I'm going to go through this so fast that I'm just going to scroll down to the bottom of it. If you're an Erlang programmer, or an Elixir programmer for that matter, you can create these things called supervisor trees. So a process spawns another process, and if that process fails, it can either restart just that process, restart that process and everybody on the same level in the hierarchy, so all of its child processes, or just the child processes that were younger than this child process. So that if one of these failed, a bunch are restarted, but not the entire program. So these restarting mechanisms are part of the language, or part of the language infrastructure. So if you really want to do process by process restarting, ideally you would want language support for it. Doing it in something like Go, you'll have to send a bunch of I am alive messages from all of your processes to and create your own supervisor tree, which is a bit of a pain. So if you have a language with language support for process supervision and you think that writing acceptance tests is easier than error handling and you don't trust yourself to not add bugs to your code, which is a very reasonable thing to not trust yourself with regard to, then acceptance tests and supervisors is a much more sensible, approachable, and resilient way of doing error handling than the traditional check for error, handle it approach. So, next week, hopefully I'll make the lecture for next week, otherwise it will be in 2 weeks. I'm going to summarize the contents of these 3 lectures and put them into a context which is a higher level of abstraction. So I want you to, for next week, think about all of these things where I've said do this or don't do this. find out what is the one thing that is common among all the things that I've told you that are good practice versus bad practice. Like what is the criteria for good practice? Because as it so happens, there's one criteria that encapsulates all of these things, which is really cool. And that's going to be the topic for next week. Once you know what that criteria is, you'll see it happen everywhere, and your ability to analyze code quality will just be taken to the next level, because it's incredibly elegant. It's not my idea, I just stole it.